Hello everybody and welcome to day 21 of climate change. Last time we were together we read through topic 1 from the IPCC summary report. Today we're going to wrap up unit 2 by learning about the other CO2 problem. Come on along. Our quote for today comes from the Prime Minister of Bangladesh, Sheikh Hasina, who says, "The situation would become disastrous with even a meter of sea level rise due to global warming, as it would inundate a fifth of Bangladesh, displacing nearly 30 million people and leading to mass movement of people." By the end of today, you will be able to explain contemporary trends in ocean chemistry. A couple things to keep in mind is that we do have our Unit 2 test coming up on Class 23. It is Class 21, which means next time we're together, we will be in review. You have a couple of labs going on right now, and I'm going to give you one more to work on today. The CO2 that we emit into the atmosphere has to go somewhere. It does not all stay in the air. Some of it gets absorbed by trees and other plants, but somewhere between a quarter and a third of it ends up being absorbed by the ocean. Unfortunately, when CO2 dissolves in water, it creates carbonic acid. And this is why when you create sparkling water, it's acidic. It tastes slightly sour. That acidity has consequences. If you notice on the other slide, I did say it creates carbonic acid and some other things. And so I want to walk you through the carbonate buffer system, which is the buffer that we're concerned with when looking at ocean pH. Some of the CO2 that dissolves in the water forms carbonic acid. And because carbonic acid is a weak acid, some of it dissociates into hydrogen ion and bicarbonate ion. And because this is an equilibrium, that some of that bicarbonate ion will dissociate into carbonate ion and an additional hydrogen ion. So whenever we add more carbon dioxide to the water, more carbon dioxide will react with water, forming more carbonic acid. When we have more carbonic acid, more of that will dissociate, and we'll have more bicarbonate. And when we have more bicarbonate, more of that will dissociate into carbonate. Seawater is a buffer. That means it resists changes in pH. This is because carbonic acid is a weak acid. And whenever you have a weak acid in equilibrium with its conjugate base, you get a buffer. For every one carbonic acid that I add to the system, I get less than one bicarbonate out because some of it still stays behind. Let's take a look at how that works in detail. Because this is not a chemistry class, I am not going to have you do calculations on this. However, I do want you to understand what's going on. Henry's law governs the dissolution of CO2. The greater the partial pressure of carbon dioxide as a gas, the greater the concentration of aqueous carbon dioxide in solution. And you can actually calculate this. If I increase my partial pressure of carbon dioxide to some amount, based off of Henry's constant, how much carbon dioxide should be dissolved. The more CO2 in the atmosphere, the more of it's able to dissolve into the ocean. That carbon dioxide that's in the ocean exists in equilibrium with carbonic acid. The carbon dioxide reacts with water to form H2CO3. Because the hydration equilibrium constant is less than 1, most of the carbon dioxide stays in carbon dioxide form. Only a small portion of that actually forms carbonic acid. Carbonic acid itself is a weak acid. The dissociation of carbonic acid into bicarbonate and H+ is not even close to complete. The acid dissociation constant is less than 1. So we have a less than 1-to-1 ratio of carbonic acids added to hydrogen ions produced. From this portion of the equilibrium, we can determine what the pH of the ocean should be using the Henderson-Hasselbalch equation. The pKa for the carbonic acid is 3.6, and then you take that, and when you add that to the log of the bicarbonate over the concentration of the carbonic acid, you can determine the pH. Because these are in equilibrium, it takes a big increase in carbonic acid to have a large change in the pH. If you do these calculations, you won't get the actual pH of seawater. It'll be pretty close, but there are other factors in play as well. When you first look at that, it might sound like a good thing. The more carbon dioxide that's in the air, the more will dissolve, the more carbonic acid will form, the more bicarbonate will form, the more carbonate will form. And I know that a lot of marine organisms form their shells or skeletons out of calcium carbonate. So the more carbonate that's available, the easier it should be to grow a shell. This should be good for our oceans. This should be good for life. Unfortunately, there's one other piece to the puzzle that throws a wrench into things. And that is the fact that calcium carbonate dissolves under acidic conditions. As we lower the pH of the ocean, the solubility of calcium ion increases. This is more able to dissolve the more acidic the ocean is. So as we build up hydrogen ion, hydronium ion concentration, we are decreasing the ability for calcium and carbonate to come together to form a shell. This has huge implications. I want to show you a little video of some of those implications so you can take a look at how this can impact humans. Before you watch the video, I do want you to remember that pH is a logarithmic scale. So the difference in pH between 8.1 and 8.0 is less than the difference in pH between 8.0 and 7.9. So that's just something to keep in mind as we watch.
In Antarctica, few animals can survive the howling winds and frigid temperatures up on the land blanketed by snow. But here in the Southern Ocean, under the serene, cool blue ice cover, Antarctica is teeming with life. In these frigid waters live creatures that would feel right at home in a 1950s monster movie. Giant sea spiders, jellyfish, anemones, and sea urchins.
They're living in water that's so cold that you can't even put your hand in it for 5 seconds without feeling extraordinary pain. It's just like right above the freezing point of seawater. It's so cold.
Today, the ability of these animals to survive in sub-freezing waters is being tested by a new threat, ocean acidification.
The Antarctic and the Arctic are thought to be possibly some of the more vulnerable marine ecosystems to climate change. And they might be the first in time to really have acidic waters meet the organisms that live there.
What's making the oceans more acidic? Scientists blame the carbon dioxide created by the burning of fossil fuels. The CO2 goes into the atmosphere, but as much as 30% is then absorbed by the oceans. The more carbon dioxide, the higher the acidity.
Initially, scientists welcomed this absorption of carbon dioxide by the oceans because they believed it would reduce CO2 concentrations in the atmosphere. But as the oceans take in carbon dioxide, now the question for scientists is how much is too much?
We knew that we were burning things to make energy, and that carbon dioxide, some of it was ending up in the oceans. And for many people, that was seen as a good thing. What we're recognizing is that there are changes in the composition in the oceans.
In the last 150 years, as CO2 has increased in the atmosphere, the pH of ocean surface waters has dropped by around 0.1 pH unit. That's a 26% increase in ocean acidity. And the Intergovernmental Panel on Climate Change predicts an additional drop of 0.2 to 0.3 pH units by the end of the century. That's a 100 to 150% increase in ocean acidity since before the Industrial Revolution. As the ocean becomes more acidic, it makes it harder for marine animals that build their shells out of calcium carbonate, like corals and oysters. At the University of California, Santa Barbara, scientists are studying the effects of higher CO2 on sea urchins.
We mix the carbon dioxide into our seawater tanks to mimic future high CO2 oceans, levels that we thought would go to in 100 years or something. And we do start to see effects at those high numbers in terms of slowing down their growth. They are a little bit smaller at any time in development. And also there's some effects on fertilization, we think, when water gets really acidic.
Not far off the coast of UC Santa Barbara, ocean acidification could have a direct impact on people who make their living harvesting sea urchins.
My name's Bruce Steele. I'm a commercial sea urchin diver. I work at the Channel Islands, which are right here off the coast.
The boom for sea urchin sushi started with the Japanese back in the 1980s. Now the uni crop brings the state of California over $100 million a year and provides essential jobs to hundreds of divers and processors. But the changes to ocean chemistry have them worried.
The problems that we're seeing with animals like sea urchins or oysters are kind of a harbinger of problems that might be going on in the open ocean.
Two recent events clearly show that ocean acidification has already arrived on western shores and could have a direct impact on the seafood we eat. In 2007, Science magazine reported that surface water in places along the California coast was already more acidic than researchers predicted. Around the same time, news reports started trickling in from oyster hatcheries in Oregon and Washington state. Millions of larvae were dying. The culprit, ocean acidification.
It seemed that it was actually the change in the chemistry of the seawater that was killing the larvae.
The massive die-off alarmed both the seafood industry and scientists. In California, they joined forces to do something about it. They're sharing data and standardizing water measurements to determine which species are most vulnerable.
There's a crew of us, the oystermen, the fishermen themselves, scientists and other people in the community are getting together and kind of asking, how can we work together to address some of these growing economic issues?
Back in Antarctica, where scientists predict acidic conditions will be felt first, the options for Gretchen Hoffman's sea urchins are quickly dwindling.
It's kind of like a double-edged sword. They've learned to live in a really cold environment that stays cold all the time, and then here comes climate change. So the ocean's going to warm and the pH is going to change. And where are you going to go? Where can you migrate to that's colder if you're an Antarctic urchin? Well, nowhere, actually.
Since the beginning of planet Earth, animals have adapted to changing conditions. But adaptation can take thousands, even hundreds of thousands of years. Now, with millions of tons of carbon dioxide going into the oceans every day, can the creatures of the sea change quickly enough to survive in the changing oceans?
I show you that because a lot of the times when we talk about ocean acidification, we only really think about how it impacts coral reefs and the beauty of them. But I do not want you to forget that it does impact the ecosystem services that many people depend upon. The National Oceanic and Atmospheric Administration has put together this really cool tool for understanding ocean and coastal acidification. What I want you to do is I want you to go into the program and I want you to work yourself through levels 1 through 5, paying attention to the magnitude of the phenomenon, the impacts of the phenomenon, and working on the embedded questions, their answers, and their rationales. Level 5 is going to ask you to explore data, and you will be writing a lab report based on this data. The example given in Level 5 uses the Gulf of Maine. However, there is data from other locations, and the choice of location that you should use is up to you. I want you to explore what's available in there, and then ask a question that you have interest in that can be answered by that data. Ask the question, come up with your hypothesis and your null hypothesis, and then extract the data you need to answer it. In your lab report, you're going to analyze that data and come to a conclusion. Well, that's it. You've now completed all of the material for Unit 2. You should at this point be able to explain to somebody the contemporary trends in climate change. I also want you to not forget about the fact that temperature is not the only important factor. It's about energy, and then we also have the other factor of ocean acidification to worry about. Come to class, we'll talk about this, and then it'll be time for review. Bye-bye, everyone.